to the organizers for giving me the opportunity to be here to replace my supervisor who couldn't come to this event. So with this talk,
which was?
Philip.
Okay.
Yeah, it's not just a group. With this talk, I would like to speak about an experimental entanglement of temporal orders, which is a relatively new result that we had. Indeed, actually, this paper has been in the archive already since long, and some of you in the audience here have already seen my talk. But what I wanted to say is that actually the paper changed quite a lot from them. We kind of partially rewrote it, so it's a very different narrative now. And this is the most recent version that will appear hopefully soon in the archive.
Try to turn it on. Maybe
it's on. Okay. No, it was the. Okay, so as we have heard already several times today, the idea behind this work is that, yeah, typically in all well-established theories, it is assumed that there is a well-defined temporal order between the events. However, it was realized in this, for example, in these three works that I'm listing here, that actually quantum theory seems to predict the existence of processes which do not have a well-defined causal structure. So we have already heard what this means, so I will go kind of fast through that. The idea is that a genuinely indefinite causal structure is a causal structure in which there is a superposition between two or more permutations between two events, for example. So the idea is that, supposing, for example, that I have a target system, and now I restrict to only the case of two parties, Alice and Bob, and I suppose that I want to send this target system through both of them. Now, of course, I will have to go either through one order or the other. If I choose to whom send it first with a classical system, for example, a classical coin, then I will send it, I don't know, to Alice first and then to Bob when it's tail, or to Bob first and then to Alice when it's head. Now, of course, if instead of choosing a classical system for my control, I choose a quantum system, then I can put the two orders in a quantum superposition. And so, for example, having a control system of the type 0 plus 1. Now, in this case, I will have a genuinely indefinite causal structure, meaning that I will not have a well-defined situation in which Alice acts before Bob, Bob acts before Alice, nor any convex mixture of these two. So not anything of this form in which with classical probabilities Alice acts before Bob or Bob acts before Alice. Now, so this is just to give a very brief idea of what this is. And how can we test this, for example, in a lab? The idea is that one can imagine that, for example, just as much as one can test entanglement via violating Bell inequalities or via an entanglement witness, also indefinite causality can be tested in a lab via some so-called causal witness, or by a violation of, could be via a violation of causal inequalities. Now, with the causal witness, it was indeed done. So we have indeed built a causal witness starting from the knowledge of process matrices and knowing that they form the causally non-separable process matrices form a closed convex set. We have found a causal witness for that, and we have indeed experimentally, both in Vienna and also in Brisbane, demonstrated experimentally that, yeah, we can build in a lab processes that do exhibit via causal witness indefinite causality. However, as I was saying, this all causal witness was constructed by using the knowledge of process matrices. And so starting from the assumption that indeed you can apply quantum mechanics to causal processes. So the idea is, the question that then we were asking ourselves is, since Oreshkov, Costa, and Bruckner proposed causal inequalities, which are a device-independent way of testing, so different from what the causal witness is, which is strongly depending on the theory, since we are using the concept of process matrices, the causal inequalities would only use measured probabilities between outcome of parties measuring in local laboratories. And yet, we didn't find a way to experimentally implement a violation of causal inequalities. So this seems to preclude the possibility to actually experimentally show in a theory-independent way that we can observe causal indefinite processes in a lab. So the question that we asked ourselves if it is at all possible to build a test to prove in a theory-independent manner, so not as we would do with a causal witness, that indeed you can observe in a lab indefinite causal processes. And this is basically what I want to show you with this work. So in this talk, I would like to show you that there is a possibility to give an affirmative answer while not violating causal inequalities. And this is by adapting Bell inequalities via no-go theorem to be applied to causal inequality, to causal structures, sorry. And just to outline this idea, I will present first this no-go theorem for temporal orders. Then I will explain you the experimental realization of that and the results we have obtained, and then some outlook and perspectives. So the idea is, okay, so the no-go theorem I'm going to present now, it's an adaptation from an original idea that was reported in this paper here, which was originally applied for gravitational masses. So we now consider a state omega, which is composite of a control and a target system. The control is what will govern the order. The target is the degree of freedom on which Alice and Bob will operate. But because I want to apply it to a Bell test, of course I will have two copies of this switch. So not only one switch, but two copies of it. And this is what we have called entangled quantum switch. Now, I will build this no-go theorem. And basically, the idea is I will present some assumptions. And I will show you that through this theorem, basically, there is no state, set of transformation and measurements which obey this assumption that can result in a violation of a Bell inequality. So if I can violate a Bell inequality, it means at least one of the three assumptions must be wrong. And then I will go through each assumption at a time, okay? So now my assumptions are that the initial joint state of the target system is local. So it does, the initial state of the target system does not violate a Bell inequality. That the laboratory operations are local transformation of the target system. So the operations of Alice and Bob into two switches do not create an entanglement, do not perform a coupling between control and target, and that the order of local operations of the two target systems is well defined. So so all the proofs I'm trying to do are going to be outside the quantum theory. However, just to give you an idea of how this works, I want to first explain it within the quantum mechanical framework, and then I will show you the proof, which is in a more generalized framework. So within quantum mechanics, why does this work? As I was saying, I want to generalize the switch to two copies of the switch. So I will have two Alices and two Bobs. And I will have two control qubits and two target qubits. So just a generalization of what I was saying before, if I have that the control qubit is in the state 0, 0, then I will send it to the two Alices and the two Bobs. And if it's in 1, 1, to the two Bobs and then the two Alices. So I can create quantum superposition, for example, sending a Bell state of the type 0, 0, minus 1, 1. I will send it through the switch, and then I will give it to some parties to measure, to perform a Bell test on the target system. OK, so I send the initial state, which is, because I want to verify assumption 1, is separable in the target and in the control as the form that I showed you there, so 0, 0, minus 1, 1. Now, there is an entanglement here in the control, and the control governs the order in which the operations are applied. So depending on this control, when the control is 0, I will send, as I was showing you before, Alice will act before Bob. And when it's 1, Bob will act before Alice. And then, in order to erase the which path information, I'm gonna project on the state of plus minus of the control qubit. And for example, looking at the outcome plus, I will obtain an outcome of this form. And then I have to do an appropriate choice of unitaries that has to be such that if the two gates are applied in one order or in the opposite order to the same state, are going to give rise to orthogonal states. So for example, this is a possible choice. And And so I will obtain a state of this form for the specific choice that I had done, where L and R, for example, is 0 minus I1 over square root of 2. So this is a Bell state, as you know, and so it should be able, in principle, to violate a Bell inequality. And so this I could use to test my no-go theorem, and then this would invalidate my no-go theorem, so it would tell me that at least one of the assumptions must be wrong. So this would work basically through a transfer of entanglement between one degree of freedom to another, just through a quantum switch. So this is the working principle behind this, the transfer of entanglement that goes from the control qubit to the order of the application of the gates to the target qubit. And so this was my no-go theorem. Now, this is just to give you a taste of how it looks in the lab. It's a photonic experiment, and it's performed with single photons, and I'm encoding the target system in the polarization of the photon and the control in the path. And the operations are applied, just some unitaries that are performed with some wave plates, and the measurement operations are performed with wave plates and polarizing beam splitters. Now, the step one is the violation of the no-go theorem, as I was saying. So performing a Bell test with the output target system, I do observe a violation by about 7 standard deviations. So this, I also did a double check within quantum mechanics with a quantum tomography, and indeed I did observe that I had RR minus LL. So this tells me that, yes, the no-go theorem is violated. And so this tells me that at least one of the 3 assumptions must be wrong, or more. So now I go to check each assumption at a time. Now, assumption 1 is relatively straightforward. I just want to check that the input state is separable. To do this outside the quantum mechanical framework, I can, for example, look at the probabilities of the joint outcome and the product of the 2 marginalized probabilities. By the very definition of separability, I should have that if my state is separable, the joint probability of outcomes in switch 1 and 2 should be equal to the product of the outcomes from switch 1 and switch 2. And indeed, I observed this experimentally. So I did all the measurements for the joint outcomes and the product of the 2 marginalized ones. And I have observed, indeed, that they are compatible within 3%, which is compatible with experimental imperfections. So this seems to prove that, yes, assumption 1 is verified. I was sending inside a separable state. OK, now I have assumption 2 and 3 to verify. Just to remind you, assumption 2 was that the operations of Alice and Bob do not couple, do not create entanglement. And assumption 3 was that the order was well defined. Now, this is a little bit the tricky point, because as I was showing you, when I was explaining you within quantum mechanics how this full scheme works, I was telling you that this works through a transfer of entanglement. So a transfer of entanglement, of course, happens thanks to Alice and Bob that are performing this operation that transfer the entanglement from the control to the target. And this happens when I have basically a quantum switch, so what I want to claim to be a quantum superposition of the order of these gates. So it is a little bit tricky to actually test these 2 assumptions separately, because they are very much related to each other. So what I'm going to do instead, I'm going to try to test them jointly. So for example, I want to see, in the case in which assumption 3 is right, so in the case in which my order is well defined, what happens to assumption 2? OK, now to do so, I will use just one switch. In fact, a no-go theorem in general, just as much as a Bell theorem, for example, can do with the assumptions of the Bell theorem, cannot really tell you which of the assumptions is wrong. Once you violate the theorem, it says that the conjunction of the assumption is wrong. And this is what I could do so far. I could say, oh, OK, I have violated the theorem, so the conjunction must be wrong. At least one must be violated. And now, basically, what I do is I move to the single switch, and I try to understand, to do further tests to understand which assumption may hold and which assumption may not hold. And in particular, for example, what I can do is I can remove Alice and leave only Bob and check if the operation of Bob couples the 2 degrees of freedom. Same way, I can remove Bob and leave Alice and check if the operation couples the 2 degrees of freedom, which shouldn't, because basically I'm sending a just a state, and I'm performing a unitary over it. So whatever unitary I can do, it doesn't really couple. And even experimentally, it's just basically a state that passes through a waveplate, and the waveplate by construction doesn't really change the path. It's only going to change the polarization.
I'm sorry, removing Bob actually means having Bob do the identity transformation.
Yes, exactly. Like here, there is just a hidden channel where that just goes through it. It doesn't do any operations. Yes, exactly. Yes, so unfortunately I cannot show you these results because I'm taking them in these very days. So this was exactly what I was telling you. Hopefully in a few weeks you will find the paper in the archive. But, well, I mean, all the preliminary results do prove that indeed a waveplate does not change the path of the photon when it passes through. And so there is really no coupling between the 2 degrees of freedom. And so this preliminary result that I obtained and final result that I obtained in the end will indeed show that there is no coupling when only Alice is there and when only Bob is there. There is no coupling between the 2 degrees of freedom. Then the idea is, which we prove mathematically in the paper, that any ordered sequence of non-entangling operations is also a non-entangling operation. So if I have Alice that is non-entangling and Bob that is non-entangling, any ordered sequence between them is still going to be overall a non-entangling operation. So this tells me that basically if 3 is right, so if it is a well-defined ordered, since I have proven that only Alice and only Bob, they do not couple, there is no way in which I could violate this no-go theorem. So basically this tells me that if 3 is right, 2 must be right. And so by equivalence, that if 2 is wrong, 3 must be wrong. Now, because I said that at least one of the 3 assumptions had to be wrong, and I've proven that assumption 1 is right, the only 2 options are that either 2 is wrong, but then this automatically means that 3 is wrong as well, for what I've just shown you, or 3 is wrong. But in both cases, 3 is wrong. And so in both cases, the scenarios in which the operations are applied in a well-defined order are to be excluded. And so this basically concludes the proof of, without having used the quantum framework, so without having used the assumption that you can indeed apply causal orders to the quantum formalism, which we can observe them in the lab. And so, yeah, with this I conclude, and I just wanted to, summarize, but doesn't matter.
Okay, that was fantastically on time, so let's our questions.
Yeah, well, I don't know, Carlo? Okay.
Yeah, coming back to Marco's talk, I guess what you're checking here in terms of causal orders is rather what you call circuit.
Yes, exactly. When he was saying that these are...
Sorry?
Yeah, no, finish your question.
Yeah, no, I mean, that's just that was basically the first part of the question, so I guess that's yes. Then testing, I mean, since it's a bit like testing valid inequalities, and with valid inequalities there's all these kinds of loopholes. Is there anything similar here?
Yeah. I mean, all the
loopholes
prosaic loopholes apply to this case as well. And additionally, further loopholes, for example, you may want to build the 2 switches state-like separated, and like there are all the standard loopholes, so for sampling and everything. Additionally, also you may want the switches.
Giulia, I'm struggling to understand the story of the indefinite causal order, and I thought I was beginning to understand it, and you threw me again. So tell me what I'm wrong. What I hear, and obviously I'm doing something wrong. What I hear is it seemed obvious before that there should be a definite, well-defined causal ordering, but look, we found a way of doing definite causal ordering. In fact, we can prove that obvious thing was totally wrong to start with. Plainly in quantum mechanics, it's clearly in quantum mechanics that indefinite causal ordering, in the sense that Marco, for instance, was saying, it's perfectly compatible with normal relativistic causal ordering. There's nothing strange in it. It's just whatever. What's then the deal to prove it? To prove something which is obviously happening. What am I? I'm missing something. I'm clearly missing something. What am I missing?
Well, maybe obvious to you, probably.
No, everybody agrees that you can do the quantum switch in a trivial way, and there isn't anybody who is questioning that. We are questioning an intuition of 10 years ago that was wrong. So what?
Well, I don't know.
Completely
I
wrong.
think that it's obvious to everyone that you can perform a switch, for example, but it's not obvious to everyone that you can violate causal inequalities in a lab. And there is still...
Is that a subtlety which I'm missing?
Perhaps. I don't know what's subtlety, but I'm trying to understand. So I would say that, for example, we don't know if we can violate causal inequalities in a lab, and there is a lot of ongoing effort, for example, from Cyril, from Charles Lab, and from many other groups in trying to understand whether there is a process that indeed can violate causal inequalities, because from the Oreshkov-Kostab-Nuclear paper, it seems that indeed the quantum mechanics seem to predict that it should be possible, and they did find a process that does violate. Then we really didn't found a way yet, and they have been putting a lot of ongoing work in this. So is there a way and we just don't see it yet, or there isn't? This is a question, for example, that we haven't answered. I agree that for what concerns the switch, it was quite clear that it could have been possible to implement, and it was just about finding a way to implement it. And then what we learned from that was that it helped to bring the conversation further on, for example, how many events are being performed inside and stuff like this. So this helped the ongoing discussion to go further. But this was clear that there would have been found a way to perform a quantum switch. But for example, for what concerns the causal inequalities, this is far less obvious, and is much more of an open question.
Sorry, if I can interject. I think we do really need to develop a shared language to distinguish between very different levels of what we call realizing the quantum switch. So there is this kind of optical realization that happens with the ordinary physics, no strange space-time happening, and is more like whether a particular gate happens before another or not. And this may not be the thing that people in quantum gravity care, so it may be that our interest in this is mostly biased by our quantum information stuff. And then there is another level of realization that is stronger and is more like the one that was in the previous talk, the kind of the one where really somehow the supervision of the geometry in which this thing happen takes place. And this doesn't happen in ordinary quantum mechanics. So when you said, I thought I was starting to understand, I think you should stick to what you were starting to understand. That's the level that I think that's the level that is important for this community. The thing that Giulia is saying, I believe is important, but it's a bit of a different emphasis compared to this space-time picture. It's more like really like what we can do for certain quantum information tasks. So maybe, yeah.
I just want to add to this before that we still actually do not understand what is realizable in. I mean, this is just maybe repeating, like we only now understand that quantum switch can be understood as a time delocalized operations. Ogden put an effort to formalize this. And this is also not clear whether this is the exhaustive what is possible with the conventional quantum mechanics. So I think at the border, it's really not clear what is obvious and what is not, even with the standard quantum mechanics. Not to speak about Marcus extensions.
Can I interject on this? I mean, the fact that knowing quantum mechanics, you would guess all your money that the quantum cycle happen around does not take anything away from actually going and doing it.
No, sure, of course.
That's the first thing. So obviously they would do it and then it would be published in Nature for precisely that reason. It's a new phenomenon, and it's always good to check. That's one point. In addition to what Chaslav is saying, to understand what's happening with the causal inequalities, what I also find interesting in this is to understand to what degree these experiments simulate the quantum gravity processes or not. That's another point with actually Marco's talk is very pertinent to it. I'm not actually sure if we can take the simulation of the actual quantum gravitational phenomenon. But I don't think anybody is claiming right now that I mean, I think everybody in the room agrees that all these phenomena is ordinary quantum mechanics on a flat space, right?
Yeah, I think the claim is for basically what the particle experiences. So we were the first one saying this is not the gravitational quantum switch, of course, and we haven't used to make any claim on quantum gravity, of course. And the idea is that, of course, for example, a local observer being sitting on A or on B could tell the difference between the gravitational and the photonic implementation. All what we're saying is that for the quantum particle itself, which was undergoing a gravitational quantum switch or was undergoing this type of process, these quantum particles wouldn't tell the difference because it would experience basically A happening before B in one branch of the superposition and B happening before A in the other branch, and then would recombine just as it would be in a gravitational. But of course, many observers, local observer, global observer, could tell the difference. So this is not a one-to-one conversion to the gravitational quantum switch, but yet we think that for the quantum particle, what happens is the same. So it's not simulating, it's really experiencing that it's the same thing. But of course, they're not the same type of process, as probably Giulia was saying also in the morning today.
Yeah.
I mean that they are not the gravitational quantum switch and they are not one-to-one, of course.
And on that note, I would conclude today. I know that there are a lot of stuff we want to discuss, but I think this for me is the clear sign that there is a desperate need of a community effort to find the right words and not to spend all our time, every time say, oh, but you meant this thing and I meant another thing with the same word, and we just kept going. So we really need, and that's probably the place where these things should happen, kind of defining and attaching words to these different levels of realization, saying, you may be interested in A, B, C, and A, B, and C are three different things. They are not the same thing. And okay, but this will require time, so let's not do it now. We have basically 55 minutes for lunch if we really want to keep the schedule tightly. So I would really suggest that we continue over lunch. Now, the rest